This is build a molecule tutorial for ClF3, chlorine trifluoride. So how to calculate certain things is for number of electrons, you look at the group number of the element. If there's any subscripts, you multiply, and then you just add it all. And for formal charge, it's valence electrons minus non-bonded electrons plus the total amount of bonds. And the best charge for formal charge is 0. And just some miscellaneous information is the name is chlorine trifluoride, ClF3, and its uses are in rocket fuel and processing nuclear reactor fuel. We're going to calculate the number of electrons in ClF3. So I'll have a periodic table somewhere up here, but it's in group 17, meaning it has 7 valence electrons, both chlorine and fluorine. So for chlorine, that'll be 7. For fluorine, that will be 7 times 3, because we have subscript of 3 right here. And 21 plus 7, that'd be 28 total electrons. Now we're going to find the arrangement of atoms. So chlorine here is the central atom. So chlorine will be in the middle, and it has 3 fluorines. So 1, 2, 3, fluorine, fluorine, and fluorine. So now we're going to draw the Lewis dot structure. But before we do that, we need to know the formal charge. And ideally, we want the formal charge to be equal to 0. And how to solve for that is number of valence electrons minus number of bonds plus non-bonded electrons. So let's first solve formal charge for chlorine. We know chlorine's valence electrons are 7. So we do 7 minus, and then number of bonds plus number of non-bonded electrons. So we see here that chlorine has 3 bonds, so we can write 3, and number of non-bonded electrons, well, we can see it has to be 4, because 7 minus 3 is 4, and we need another 4 to be subtracted from it to give a formal charge of 0. Now for fluorine, we can do the same thing. So fluorine has 7 valence electrons. It has 1 bond, and that means 7 minus 1 is 6. And that means we'll need 6 non-bonded electrons on fluorine. So we'll get 6 there, and we'll get 0. So these are the numbers we're going to have. We're going to have 3 bonds for chlorine, 1, 2, 3, and 4 non-bonded electrons. So that's 2 non-bonded electron pairs. And for fluorine, we're going to have 1 bond, and we're going to have 6 non-bonded electrons. So that's 3 electron pairs. Let's begin drawing. So fluorine, chlorine, fluorine, and fluorine. So just a few seconds ago, we said fluorine's going to have 6 non-bonded electrons. That means 3 lone pairs. So 1, 2, 3. And so fluorine's formal charge will equal 0. And that will be the same for all of the fluorines. So all the fluorines will have 6 electrons on it. And we said last time chlorine's going to have 2, 1 there and 1 there. And this just represents 2 electron pairs. So this is the best structure for chlorine trifluoride with formal charges of fluorine and chlorine equaling 0. Now we're going to find resonance of this. Now resonance is basically, it can take on another sort of arrangement. Here we have the same arrangement, but this time we can do a double bond on any of the fluorines. So I'm going to choose to do a double bond here. So to find 28 electrons, we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And here we have one of the resonance structures of chlorine trifluoride. What we can do is we can actually move this double bond all around, so it's also the same as chlorine 1 bonded. We'll have 1, 2, 3, 4, 5, 6. A double bond here for fluorine with only 2, and then this also has 6 with 2 lone pairs. And also we can move it here again. So then just do double arrows with chlorine 1, 2, 3, 4, 5, 6. Fluorine, 1, 2, 3, 4, 5, 6. And a double bonded fluorine here with only 2. So these structures are all the same. Chlorine trifluoride exhibits resonance. Now we're going to find the hybridization energy of chlorine, and we're doing chlorine because it's the central atom. So we're only interested in this last part here. So we have our s orbital, and then we have our p orbital. So chlorine is 3s, the last part is 3s2 and 3p5. So 1, 2, 3, 4, 5. Now, to find the hybridization energy, we do the same thing down here. I'll just do that. And now we have the d orbital. And what we do is we take this one, this one, this one. So anyone that has a pair, we remove it all the way to the front. So it'll be that, 1, 2, 3, and moving 3 to the front. So 1, 2, 3. So it will become sp3. Well, we can do s1, but that's the same thing, it's just s. So then p3, because it has 3, and then d3. So that's the hybridization of chlorine. Right, now it's time to decide if this is polar or not. And it does have this which blocks it here, which this blocks it, and that blocks it. But the only thing that makes it polar are these lone electron pairs. So 1, 2. So there's 2 lone electron pairs, and that's what makes chlorine trifluoride polar. So here's my 3D model. And continuing from the whiteboard, you can see that it has 2 lone pairs, which means it is polar. And the molecular geometry is a T shape because it makes a T, and electron geometry is trigonial bipyramidal. And for the bond angles, this is 90 and this is also 90. So the bond angles for this are 90.